Hello, in this lecture we'll answer two questions. The first question, we find out the area of this green shape using two different methods. And the second question, we find out the radius of this semicircle that is described by this rectangle after ABCD. We'll start with the first question. In the drawing, we have rectangle ABCD. Know that side AB of rectangle ABCD equals to 3 units in its length. This is line segment AE that equals to 1 unit in its length. Inside this rectangle we have this green shape. The green shape is actually triangle BEC. This is angle BEC that equals to 45 degrees inside. Again, our task is to find out the area of this green shape is actually the green triangle BEC. So we start with the first method. First of all, ABCD is a rectangle, therefore all those four angles are right angles. So this is a right angle. This is also a right angle. This is a right angle. This is also a right angle. We also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB equals to the opposite side DC, but AB is 3, therefore the opposite side DC must be also equal to 3 units in its length. The next step, we will define this line segment ED as X. So side AD in total equals to 1 plus X. So according to the formula that says that the opposite sides of rectangle are equal to each other, side AD equals to the opposite side BC. But AD equals to 1 plus X, and therefore the opposite side BC must be also equal to 1 plus X units in its length. In the next step, we will do a construction. That is to say, from point E, we will do a perpendicular on BC. Again, from point E, we will do a perpendicular on BC. So actually, this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to our construction. We define the touching point of the perpendicular from point E and BC. This point is point S. By doing this construction, we can do quadrilateral ABSC. Inside this quadrilateral ABSC, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. Therefore, 270 degrees plus the size of this fourth missing angle in total must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So in the small quadrilateral ABSC we have 4 rectangles. Therefore we can write to quadrilateral ABSC as a rectangle. We define the perpendicular ES as edge. It is a relation for height. It is actually ES is the height to the base BC. Is the height to the base BC of triangle PCE. So ES equals to H according to our definition. So in the small rectangle A, B, and C, the opposite sides are equal to each other. This is to say side AB equals to side ES in itself, according to the rules we mentioned. But AB equals to 3, therefore the opposite side ES must be also equal to 3 units in its length. ES equals to H, and therefore H equals to 3 units in its length. The green shape, it is actually the green triangle BCE. So our task is to find out the area of this green triangle BCE. The area of any triangle equals to the base of the triangle times the height over 2. But before that, we focus on this triangle AEB. This triangle AEB, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle AEB, AB square plus AE square equals to EB square. So what is known? This triangle AEB. Here by PT is the version for Pythagoras theorem. So in this right triangle AEB, EB square, that is the square of the hypotenuse, equals to AE square plus AB square. Okay, again, in this upper right triangle EAB, EB square, that is the square of the hypotenuse, equals to AE square plus AB square. EB is the missing side, so we leave it as it is, so it is EB square equals to AE square. AE is 1, therefore A square is 1 squared, it is 1, plus AB square. AB is 3 according to what is given in the question, so therefore AB square is 3 squared, that is 9. So today we found out that EB square equals to 1 plus 9, that is 10. So EB square equals to 10. Here we take a root out of this equation and finally get that the missing hypotenuse AB is equal to the square root of 10 units in its length. So this is the missing hypotenuse AB. This equals to the square root of 10 units in its length. Likewise, we replace the Pythagoras theorem on this right triangle ADC. The right triangle ADC, here by PT is the version for Pythagoras theorem. So in this right triangle ADC, according to the Pythagoras theorem, EC square, that is the square of the hypotenuse, equals to ED square plus DC square. Repeat again, in this right triangle ADC, according to the Pythagoras theorem, EC square, that is the square of the hypotenuse, equals to ED square plus DC square. EC is the missing hypotenuse, so we leave it as it is, so it is EC square equals to ED square. ED is x, therefore ED is x, therefore ED square is x square plus DC square. DC is 3, therefore DC square is 3 square, that is 9. So to that, we found out that EC square equals to x square plus 9. So here we take out all of this equation and find out that the missing hypotenuse EC is equal to the square root of x square plus 9. This is the missing hypotenuse EC that equals to the square root of x square plus 9. So write it down. EC equals to the square root of x square plus 9. In the next step, we'll calculate the area of this green shape. This is actually the right, the green triangle BCE in two different ways. And then we create equation that says that the area of this green triangle BCE according to the first method of calculation must be equal to the area of this same green triangle BCE according to the second method of calculation. So the area of this green right triangle BC is actually the area of this green shape according to the first method of calculation. Is equal to the base of this green triangle BCE times the height over 2. So again, according to the first method of calculation, the area of the green shape, the area of the green triangle BC equals to the base of the triangle. We choose the base as BC times the height h over 2. So the area of this green shape, the area of the green triangle BC equals to the base BC, that is 1 plus x. Times the height h is h equals to 3 over 2. According to equation 1, we found out that the area of the green shape, that is actually the area of the green triangle BCE, is equal to 3 times 1 plus x over 2. Repeat again, and we found out that the area of the green shape, that is actually the area of this green triangle BCE, equals to the base of the triangle, that is BC, times the height h over 2. So it is equals to 3 times 1 plus x over 2. In the next step, we calculate the area of this green triangle BC in a different way. Actually, we know that the area of any triangle, equals to the multiplication of the two sides by each other times the angle times sum of the angle between the two sides over 2. So this is triangle ABC that would be any triangle. Side AB equals to A units in itself, side AC equals to B units in itself, and the angle between A and B is theta. So They have this triangle ABC that could be any triangle equals to the multiplication of the two sides by each other, that is to say A times B times sinus triangle between the two sides, that is 10 over 2. So the area of this triangle ABC equals to A times B times sinus 10 over 2. And therefore, the area of this great triangle BCE or BEC equals to the multiplication of the two sides by each other, that is to say it is EC times EB times sinus triangle between the two sides, that is 45 degrees over 2. So write it down. The area of this green shape, the area of the green triangle BCE equals to the multiplication of the two sides by each other, that is to say it is EB times EC times sinus the angle between the two sides, that is 45 degrees over 2. So it is sinus 45 degrees over 2. So according to the second method of calculation, the area of this green triangle BCE equals to EB times AC times sinus 45 degrees over 2. EB equals to the square root of 10 times EC. EC equals to the square root of x squared plus 9 times sinus 45 degrees over 2. So according to the second method of calculation, the area of the green triangle BCE equals to the square root of 10 times the square root of x squared plus 9 times sinus 45 degrees over 2. The next step, we create equation 3 that says that the area of this green triangle BC according to the first method of calculation must be equal to the area of this green triangle BC according to the second method of calculation. So write it down. Equation 3 states that the area of the green triangle BCE according to the first method of calculation must be equal to the area of the same green triangle BCE according to the second method of calculation. So the area of the green triangle BC according to the first method of calculation equals to 3 times 1 plus x over 2, square it inside, and it must be equal to the area of the same green triangle BC according to the second method of calculation. The area of this green triangle BC according to the second method of calculation equals to the square root of 10 times the square root of x squared plus 9 times sinus 45 degrees over 2. Here we have 2 on both sides of this equation, so 2 will get cancelled. So you cancel 2 and this side of the equation 3 left only with 3 times 1 plus x, and is equals to this expression. Sin 45 degrees is square root of 2 over 2. So here in total we have square root of 10 times square root of x squared plus 9 times sin 45 degrees, and sin 45 degrees equals to the square root of 2 over 2. Square root of 10 times square root of 2 equals to the square root of 10 times 2, that is square root of 20. So if you found out that according to equation 3, 3 times 1 plus x equals to, again, square root of 10 times square root of 2 is square root of 20 times square root of x squared plus 9 over 2. So according to equation 3, I should found out that 3 times 1 plus x equals to, we substitute 20 by 4 times 5, so 20 equals to 4 times 5, so inside the root we have 4 times 5 times square root of x squared plus 9 over 2. The square root of 4 is 2, so we take 4 out of the root. So according to equation 3, I should found out that 3 times 1 plus x equals to, again, the square root of 4 is 2, so we take 4 out of the root. Inside the root we left only the square root of 5, and we have the square root of x squared plus 9 divided by 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. After cancel 2, we left only with 3 times 1 plus x equals to the square root of 5 times the square root of x squared plus 9. Here we will square both sides of this equation, equation 3. So 3 times 1 plus x, 3 times 1 plus x squared equals to 3 squared, that is 9, times 1 plus x squared. The square root of 5 is 5, and the square root of x squared plus 9 equals to x squared plus 9. The square cancels the root, and we left only with x squared plus 9. So I have found out that 9 times 1 plus x squared equals to 5 times x squared plus 9. Here we open the brackets on both sides of this equation, equation 3. Again, according to this equation, equation 3, 9 times 1 plus x squared. So 1 plus x squared equals to 1 squared, that is 1, plus x squared, plus 2 times 1 times x, that is 2x. The other side of the equation, we'll open the bracket, so we have 5 times x squared equals to 5x squared, plus 5 times 9 is 45. Here we open the brackets on this side of this equation 3. Again, according to equation 3, we have 9 times 1 is 9, plus 9 times x squared is 9x squared, plus 9 times 2x is 18x, equals to 5x squared plus 45. Here we subtract 5x squared from this equation 3, and get that 9x squared plus 5x squared is 4x squared, plus 18x plus 9 equals to 45. So here we subtract 45 from this equation 3, and finally get that according to this equation 3, 4x squared plus 18x, 9 minus 45 is minus 36, equals to 0. So in total, according to equation 3, we found out that 4x squared plus 18x minus 36 equals to 0. Here we divide this equation 3 by 4. If I get that according to equation 3, four x squared over 4 is x squared, plus 18x over 4 is 4.5x, minus 36 over 4 is minus 9, equals to 0. 0 over 4 is 0. So in total, we found out that x squared plus 4.5x minus 9 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. This general formula for quadratic equation, a, b, and c are the coefficients of this quadratic equation. And x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared plus 4 times a times c over 2a. In our specific quadratic equation, that is to say, x squared plus 4.5x minus 9 equals to 0. The variable that we are looking for is x. The coefficient a equals to 1. The coefficient b equals to 4.5. And the coefficient c equals to minus 9. So the only thing that is left to do in order to find out the value of x in our specific quadratic equation, we just have to put the data of our specific quadratic equation inside this general formula for x, and this way we find out the value of the values of x, because x might have two solutions. So we'll do it now, and we get that x equals to minus b. B is 4.5, therefore minus b is minus 4.5, plus minus square root of b squared. B is 4.5, b is equals to 4.5, therefore b squared is 4.5 squared, that is 20.25. Minus 4 times a times c. So it is minus 4 times A. A is also minus 4 times 1 is minus 4 times C. C is minus 9. And therefore, C is minus 9. So minus 4 times A times C is equals to minus 4 times minus 9, that is plus 36. Minus times minus plus. Divided by 2A. A is 1, so 2A is 2 times 1, that is 2. So in total, she found out that X equals to minus 4.5 plus minus 20.25 plus 36 equals to 56.25 divided by 2. So X equals to minus 4.5 plus minus. The square root of 56.25 is 7.5 divided by 2. So here you have two solutions that are possible for X. The first solution for X is that X equals to minus 4.5 minus 7.5 over 2. Minus 4.5 minus 7.5 is minus 12 over 2. Minus 12 over 2 is minus 6. So she found out that X equals to minus 6. X equals to minus 6. X is the length of this line segment AD. Again, according to our definition, X is the length of this line segment AD. So X is a length. It must be a positive number. Therefore, X can never be equal to minus 6, that is a negative number. So the first solution for X, that X equals to minus 6, is an incorrect solution and cancel the solution. And we will take into account only the second solution for X. The second solution for X is as follows. X equals to minus 4.5 plus 7.5 over 2. Minus 4.5 plus 7.5 equals to 3. So X equals to 3 halves. X equals to 3 halves is 1.5 units. So line segment AE, line segment ED is equals to X equals to 1.5 units in its length. Our task is to find out the area of this green shape. Our task is to find out the area of the green shape. The green shape, it is actually the green triangle EBC. So our task is to find out the area of this green triangle EBC. The area of any triangle equals to the base of the triangle times the height over 2. Read again. The area of any triangle equals to the base of the triangle times the height over 2. We choose the base of this green triangle EBC is BC. So the base is BC. The height is h over 2. So in total, if you found out that the area of the green shape, the area of this green triangle BC equals to the base BC. BC is 1 plus x. times the height edge is 3 over 2. We just write down from now that x is equals to 1.5. And therefore 1 plus x is 1.5, that is 2.5 times 3 over 2. 2.5 times 3 is 7.5. And 7.5 over 2 equals to 3.75 square units in its size. So if you found out that the area that we are looking for this question, that is the area of this green shape, in total is equal to 3.75 square units in its size. So we finish with the first method. In the next step, I present to you how to find out the area of this green shape according to the second method. It is given us the question that ABCD is a rectangle, therefore all those four angles are right angles. We define the length of this line segment ED as x, exactly as we did in the first method. So we know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 3, therefore the opposite side DC must be also equal to 3 units in its length. Likewise, according to the sum rule, according to the rule that says that the opposite sides of a rectangle are equal to each other, we get that side AD equals to the opposite side BC. But AD is 1 plus x, therefore the opposite side BC must be also equal to 1 plus x units in its length. BC equals to 1 plus x units in its length. In the next step, we will do a construction, that is to say from point E, we will go perpendicular on BC. Again from point E, we will go perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point E and BC, this point is point S. By doing this construction, you get the idea. The small quadrilateral ABSC. Inside the small quadrilateral ABSC, we have 1, 2, 3 angles. Therefore, this fourth segment must be also equal to 90 degrees in size. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth segment must be equal to 90 degrees in size. So inside the small quadrilateral AEBS, we have 4 angles. Therefore, we can relate to quadrilateral AEBS as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle ABSC, Side AB must be equal to the opposite side ES. We define ES as the height because it's the height to the base BS. We define the height as h. ES equals to h according to our definition. This is actually the same process that we did in the first method. So in rectangle in rectangle ASBA, the opposite sides are equal to each other. That is to say, side AB equals to the opposite side ES. But AB is 3, therefore the opposite side ES equals to 3 units in its length. So ES equals to h and h equals to 3 units in its length. So we did all the process, all the things that I did currently, we only done in the first method. Now in the second method, we do another thing. That is to say, we define this angle DEC as theta. And again, we define this angle AEB. This angle is theta. So in the right triangle, the upper right triangle ABE, tangent theta equals to AB over AE. And again, in this right upper triangle AEB, tangent theta equals to AB over AE. Repeat again, in the upper right triangle ABE, tangent theta equals to AB over AE. AB is 3, or AE is 1. So in total, tangent theta according to equation 1, tangent theta equals to 3 over 1, that is 3. So according to equation 1, we found out that tangent theta equals to 3. We have the trigonometric identity that states that tangents theta plus 45 degrees equals to 1 plus tangent theta over 1 minus tangent theta. So according to this trigonometric identity, tangents 45 degrees plus theta or theta plus 45 degrees, it doesn't matter, equals to 1 plus tangent theta. We only found out that according to equation 1, tangent theta equals to 3, so we substitute tangent theta by 3, then 1 plus 3 over 1 minus tangent theta. Again, tangent theta is 3, so we substitute tangent theta by 3. So in total, according to equation 2, we found out that tangent theta plus 45 degrees equals to 1 plus 3 over 1 minus 3. 1 plus 3 is 4, over 1 minus 3 is minus 2. 4 over minus 2 is minus 2. So in total, we found out that according to equation 2, tangent theta plus 45 degrees equals to minus 2. And according to equation 1, we already found out that tangent theta equals to 3. AD is one side of arterial ABCD, so AD is a side of arterial, it is absolutely a straight line. And again, AD is a straight line. So if you focus on the right side of the straight line AD at point E, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the right side of the straight line AD at point E? We have this is angle theta, this angle equals to 45 degrees, plus this first missing angle, in total the sum of those angles must be equal to 180 degrees according to rule 3. Therefore, this first missing angle must be equal to 180 degrees plus the sum of those two angles. That's actually theta plus 45 degrees. And again, this first missing angle must be equal to, that's actually angle DEC, must be equal to 180 degrees plus the sum of those two angles. That is theta plus 45 degrees. So, in the next step, we focus on this lower right triangle EDC. The lower right triangle EDC the tangents of this angle is actually this angle equals to total to 180 degrees minus theta plus 45 degrees. So the tangents of this angle, this side EDC equals to DC over ED. Repeat again, in the lower right triangle EDC, tangents 100 degrees minus theta plus 45 degrees equals to DC over ED. In the right triangle EDC, tangents 180 degrees minus theta plus 45 degrees equals to DC over ED. DC is 3. Over ED is X. So to that, we should find out that according to equation 3, tangents 180 degrees minus theta plus 45 degrees equals to 3 over X. We have another trigonometric identity that says that tangents 180 degrees minus theta equals to minus tangent theta. We use this trigonometric identity in order to find out what is the value of this tangents 180 degrees minus theta plus 45 degrees. According to this trigonometric identity, tangents 180 degrees minus theta equals to minus tangent theta, we will get that tangents 180 degrees minus theta plus 45 degrees equals to minus tangents theta plus 45 degrees. And again, those two expressions are equal to each other according to this trigonometric identity. This says that tangent under the integral of theta equals to minus tangent theta. Okay, and it equals to 3 over x. Equals to 3 over x. And according to equation 2, tangent theta plus 45 degrees equals to minus 2. So we can solve the tangent theta plus 45 degrees by minus 2. It's equals to minus 2. Again, that according to equation 3, we have here minus, and tangent theta plus 45 degrees equals to minus 2. So we solve the tangent theta plus 45 degrees by minus 2. And this equals to 3 over x. So to that, according to equation 3, we actually found out that minus 2 equals to 3 over x. Minus is plus. So this is 2. So in the left side of equation 3 we have 2. And minus times is 2. So in total, this expression equals to 2. And 2 equals to 3 over x. And again, we should find out that according to equation 3, equals to 3 over x. Here we multiply this equation by x. Again, according to equation 3, 2x equals to 3. Here we divide this equation 3 by 2. And find that according to equation 3, x equals to 3 halves. That is 1.5. So in total we should find out that x equals to 1.5 units in its term. ED equals to x equals to 1.5 units in its term. Our task is to find out the area of this green shape. The green shape is actually the green target EBC. So the task is to find out the area of the green target EBC. The area of any target equals to the base of the target times the height over 2. We choose the base of this green target EBC as BC times the height is h over 2. So in total, we found out that the area of the green shape equals to the area of the green target BC. The area of the green target BC equals to the base BC times the height h over 2. BC equals to 1 plus x. We just found out that x equals to 1.5. Therefore, BC in total equals to 1 plus x, that is 1 plus 1.5 is 2.5. So BC in total equals to 2.5. The base BC equals to 2.5 units in its length times the height h. H equals to 3 over 2. 2.5 times 3 is 7.5. And 7.5 over 2 equals to 3.75 units in its size. So in both methods, we have found out that the area of this green shape, that is the area that you are looking for in this question, is equal to 3.75 square inches in size. So we finish with the first question. In the next step, I present you the second question of this lecture and also the second question. In the second question, our task is to find out the radius of this semicircle. So in the drawing, we have rectangle ABCD that blocks this semicircle. Of this semicircle is inscribed by rectangle ABCD. We know that this is 97 QB. QB equals to 1 unit in its length. This is 97 PD equals to 2 units in its length. Again, our task is to find out the radius of this semicircle that is inscribed by this rectangle ABCD. So first of all, we know that all those four angles inside rectangle ABCD are right angles. In the next step, we will define the center of this semicircle. This point is point O. We will define the radius of this semicircle as x. In the next step, we will define the point of tendency of tangent DC with this semicircle. This point is point H. Likewise, we will define the point of tendency of tangent BC with this semicircle. This point is point T. And we will join points O and H together by a straight line. Point O is the center of the semicircle, point H is the point on the semicircle itself, therefore OH is the radius of this semicircle. This is equals to x according to our definition. OH is the radius of this semicircle, is equals to x. The radius OH is equals to x. The radius OH is drawn to point H, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius HO. If this is perpendicular to HO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, we will join points O and T together by a straight line. Point O is the center of the semicircle, point T is the point of the semicircle itself, therefore OT is the radius of this semicircle, is equals to x. The radius OT is equals to x, the radius OT is drawn to point T, that is the point of tendency BC with this semicircle. Whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius TO. If BC is perpendicular to TO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the sum rule 1. So in this quadrilateral OTCH, we have 1, 2 vertices. The sum of vertices is 270 degrees, so 270 degrees plus the side of this 4 again, in total must be equal to 360 degrees. According to the rule, it said that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 again must be equal to 90 degrees in size. So in quadrilateral OTCH we have 4 rectangles, and therefore can relate to quadrilateral OTCH is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OTCH, side OH must be equal to the opposite side TC, but OH is x, therefore the opposite side TC must be also equal to x units in its length. Likewise, according to the sum rule, in the sum rectangle OTCH, side OT must be equal to the opposite side HC, but OT is x, therefore the opposite side HC must be also equal to x units in its length. So in total, we found out that quadrilateral OTCH is not a rectangle but a square because of the fact that all of its sides are equal to each other. Each side equals to x units in its length. So this is the small quadrilateral OTHC, this is a square. In the next step, we will do a construction, that is to say, from point O, that is the center of this semicircle, we will do perpendicular on AB. Again, from point O, that is the center of this semicircle, we will do perpendicular on AB. So actually, this angle equals to 90 degrees in its side, and this angle also equals to 90 degrees in its side according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point L. By doing this construction, we get the small quadrilateral LBTO. Inside the small quadrilateral LBTO, we have 1, 2 furthers, and this form must be equal to 90 degrees in size. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So quadrilateral LBTO is 4 rectangles, and therefore we can relate to quadrilateral LBTO is a rectangle. This is the small quadrilateral LBTO, this is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle LBTO, side OT must be equal to the opposite side LB. But OT is x, it is the radius of the semicircle, therefore the opposite side LB must be also equal to x units in its length. It is given us the question that QB equals to 1. So what is the length of the missing line segment? Line segment LQ. LQ equals to LB minus QB. Again, LQ in total equals to LB minus QB. So it is now the missing line segment LQ equals to LB minus QB. So in total, the missing line segment LQ equals to LB, that is x, minus QB, that is 1. So if you want to know that this is the missing side line segment LQ, this is equals to x minus 1 units in its length. In the next step, we'll do another construction, that is to say, from point O, that is the center of this semicircle, we will do perpendicular on AD. Again, from point O, we will do perpendicular on AD. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point O and AD. This point is point Z. By doing this construction, we created the small quadrilateral AL or Z. Inside this small quadrilateral AL or Z, we have 1, 2 vertices, and therefore this fourth missing must be equal to 90 degrees in size, according to the rule that says that the sum of the areas in any quadrilateral is equal to 360 degrees. So inside the small quadrilateral AL or Z, we have 4 vertices, and therefore can relate to quadrilateral AL or Z as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle AL or Z, side AL must be equal to the opposite side OZ. Okay, we don't know what is the length of AL, and therefore we have it as it is. So quadrilateral AL or Z is a rectangle. And here we have, by doing the construction, we created another quadrilateral. This is the lower quadrilateral OZDH. Inside this lower quadrilateral OZDH, we have 1, 2 vertices, and therefore this fourth must be equal to 90 degrees in size, according to the symbol that says that the sum of the areas in any quadrilateral is equal to 360 degrees. So inside quadrilateral OZDH, we have 4 rectangles, and therefore we relate to this quadrilateral OZDH as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OZDH, side OH must be equal to the opposite side ZD. But OH is x, OH equals to x, and therefore the opposite side ZD must be also equal to x units in its length. The opposite side Z must be also equal to x units in its length. What is the length of this missing line segment? Line segment ZP. From the drawing, it is very easy to see that ZP in total equals to ZD minus PD. So if you know, the missing line segment ZP in total equals to ZD minus PD. So the missing line segment ZP equals to ZD, that is x, minus PD, that is 2. So this is the missing line segment ZP, that equals to x minus 2 units in its length. This is the angle ZOT. Angle ZOT total equals to 90 degrees plus 90 degrees, it is 180 degrees. And we know that any angle that is equals to 180 degrees in its size is defined as a straight line. Therefore, ZOT is a straight line. because of the fact that angle ZOT is equal to 180 degrees in its side, therefore ZOT is a straight line. Therefore ZT is also a straight line. ZT is a straight line. And because of the fact that ZT is a straight line, this is shape ABTZ. Shape ABTZ in total equals to S1, 2, 3, 4 sides. So it is not. This is the shape ABTZ. Shape ABTZ is 4 sides. Yeah. Shape ABTZ is 4 sides. Therefore, shape ABTZ is a quadrilateral. Shape ABTZ is a quadrilateral because it has 4 sides. So, in this quadrilateral ABTZ, we have 4 right angles. 1, 2, 3, 4. Any quadrilateral that has 4 right angles, it is defined as a rectangle. Therefore, quadrilateral ABTZ is a rectangle. Because it has 4 sides and 4 right angles. This is quadrilateral ABTZ, that is a rectangle. But we also know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABTZ, side AB is parallel to the opposite side TZ. In rectangle ABTZ, side AB is parallel to the opposite side TZ. Okay, side AB is parallel to the opposite side ZT. So here you can implement rule 10. Repeat quickly on rule 10. According to rule 10, corresponding angles between parallel lines are equal to each other. So in the drawing we have line 8, it is parallel to line B. Those two angles are both defined as corresponding angles and they are located between the parallels A and B, and therefore they must be equal to each other in their sizes. This is to say, those two angles are equal to each other according to this rule, rule 10. Likewise, those two angles are also defined as corresponding angles and they are located between the parallels A and B. Therefore, they must be equal to each other in their sizes. You can see that those two angles indeed equal to each other in their sizes according to this rule, rule 10. So we can actually implement rule 10 in our drawing. In our drawing, AB is parallel to ZT. AB is parallel to ZT. So those two angles are defined as corresponding angles. Repeat again. those two angles are defined as corresponding angles, and they are located between the parallel lines AB and ZT. Actually, this is the third line QP that is defined as transversal. Again, AB is parallel to ZT, and the third line QP is defined as the transversal. And because of the fact that those two corresponding angles are located between the parallel lines AB and ZT, they must be equal to each other and their sizes, according to Rule 10. So if we define this angle, the local angle LQO as alpha, then this angle ZOP must be also equal to alpha because they are equal to each other according to Rule 10. In this right triangle OLQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, the lower triangle ZOP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha according to the same rule. That said that the sum of the angles in any triangle is equal to 180 degrees. What is the definition of line segment OP? Line segment OP starts from the center of the semicircle, that is to say from point O, and ends at point P, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OP is the radius of this semicircle, equals to x according to our definition. Likewise, what is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of this semicircle, and ends at point Q, that is the point of the semicircle itself. Therefore, OQ is also the radius of this semicircle, equals to x. In the next step, we will prove that the right grand triangle LOQ can point to this right lower grand triangle OZP, according to angle side angle rule. So write it down. We have to prove that those two right grand triangles can point to each other. So we have to prove that the upper right triangle LOQ, the upper right grand triangle LOQ can go into this right lower triangle grand triangle ZPO. And again, we have to prove that the upper right triangle LPO, the upper right triangle LOQ can go into the right lower grand triangle ZPO. So why those two grand triangles can go into each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. This is the angle LQO, in the right upper triangle LQO, and is equals to this angle is the angle ZOP, in the right lower triangle ZOP. So repeat again, we should find out that angle LQO in the right upper triangle LQO is equal to angle ZOP in the right lower triangle ZPO, they're both equal to alpha and therefore they're equal to each other. In addition, QO in the upper grand triangle equals to OP in the lower grand triangle. Read again. Side QO in the upper right grand triangle LOQ is equals to side OP in the right lower grand triangle ZPO. They are both the order of the semicircle equals to X and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees from alpha and therefore they are equal to each other. So here, this is angle LOQ in the right grand triangle LOQ, and it's equals to this angle, the angle ZPO in the right lower grand triangle OZP. And again, we should find out that angle LOQ in the upper grand triangle LQO is equals to angle ZPO in the right lower grand triangle ZPO. They are both equal to 90 degrees from alpha and therefore they are equal to each other. So we should prove that those two right triangles can go into each other according to according to angle side angle rule. So we should find out that the upper grand triangle LOQ congruent. This is the sign of congruent to the right lower grand triangle ZPO according to angle side angle rule. Those two grand triangles can go into each other according to angle side angle rule. That is to say, we should find out that those two angles and the side that is included between those two angles, that is side QO, and this upper grand triangle LOQ, are corresponding equal to those two angles and the side that is included between those two angles, that is side OP, in this right grand triangle ZOP. And therefore, those two right triangles can go into each other according to angle side angle rule. Okay, we have those two angles, the side that is included between those two angles in this triangle are corresponding equal to those two angles, and the side that is included between those two angles, this right lower grand triangle. Therefore, those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right grand triangles can go into each other, we will derive that their corresponding sides must be also equal to each other and their lengths. According to the rule that corresponding sides in congruent triangles are equal to each other. That is to say, those two right triangles can go into each other, therefore their corresponding sides must be also equal to each other and their lengths. That is to say, we conclude that side LQ is equal to the corresponding side ZO. Why side AQ is the corresponding side of side ZO? Because both of them are located in front of this area that is 90 degrees alpha. ZO also is located in front of this area that is also 90 degrees alpha. So LQ in this grand triangle LOQ is equal to ZO in this grand lower triangle ZPO. LQ equals to ZO. Again, from the fact that those two right triangles can go into each other, we will we know that their corresponding sides must be also equal to each other in their lengths. That is to say, side AQ of the upper green right triangle is equal to corresponding side ZO in the right lower triangle, ZOP. But we have already found out that LQ equals to x minus 1. So we write here that LQ equals to x minus 1. And for this equation, x minus 1 equals to LQ equals to ZQ. We have that the missing side ZQ must be also equal to x minus 1 units in its length. This is the missing side ZO. This is also equals to x minus 1 units in its length. In the next step, we will implement the Pythagoras theorem on this right green triangle ZOP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle ZOP, right green triangle ZOP, here by PT is the abbreviation for Pythagoras theorem. So this green right lower triangle ZOP, according to the Pythagoras theorem, OP squared, that is the square of the hypotenuse, equals to ZO squared plus ZP squared. Repeat again, this green right lower triangle ZOP, according to the Pythagoras theorem, OP squared, that is the square of the hypotenuse, equals to OZ squared plus ZP squared. OP equals to x, and therefore OP squared is x squared. And it equals to ZO squared. ZO is x minus 1, therefore ZO squared is x minus 1 squared. Plus ZP squared. ZP is x minus 2, therefore ZP squared is x minus 2 squared. In total, we have found out that x squared equals to x minus 1 squared plus x minus 2 squared. Here we'll open the bracket on this side of this equation and find again that x squared equals to x minus 1 squared. X minus 1 squared equals to x squared plus 1 squared, that is 1, minus 2 times x, minus 2 times x times 1, that is minus 2x, plus x minus 2 squared. X minus 2 squared equals to x squared, plus 2 squared, that is 4, minus 2 times x times 2, that is minus 4x, equal, okay. So here we have x squared both sides of this equation, so x squared gets cancelled. After cancelled x squared in the side of the equation, we left with nothing, that is to say 0. And on the other side of the equation, we have 1 plus 4 is 5. Minus 2x minus 4x is minus 6x. Plus x squared. So in total, we found out that x squared minus 6x plus 5 equals to 0. This is a quadratic equation, and the general formula for a quadratic equation is as follows. ax squared plus bx plus c equals to 0. In the general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus 4 of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared minus 6x plus 5 equals to 0, the variable that we are looking for is x. The coefficient a equals to 1, the coefficient b equals to minus 6, and finally the coefficient c equals to 5. So we have all the data that is needed in order to find out the variable that we are looking for in this quadratic equation, that is x. We just have to put the data of our specific quadratic equation inside this general formula for x, and this way we find out the value of the values of x, because x must have two solutions. So we do it now, and we get that x equals to minus b. B is minus 6, so minus b is minus 6, that is plus 6, plus minus square root of b squared. B is minus 6, therefore b squared is minus 6 squared, that is 36, minus 4 times a times c, so it is minus 4 times a is also minus 4 times 1 is minus 4, times c is 5, so minus 4 times 5, minus 4 times 5 is minus 20. So total minus 4 times a times c is minus 40, minus 4 times a times c is minus 20, so in total minus 4 times a times c is minus 20 over 2a. A is also 2 times a is 2 times 1, that is 2. So total, we should find out that x equals to 6 plus minus, inside the root we have 36 minus 20 is 16, so inside the root we have only 16 over 2. The square root of 16 is 4, so in total we get that x equals to 6 plus minus 4 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to 6 plus 4 over 2. 6 plus 4 is 10, and 10 over 2 is 5. So the first solution for x is x equals to 5 units in its length. X is the radius of this series again, that is the radius that we are looking for this question. But we have another solution for x. The second solution for x is as follows. X equals to 6 minus 4 over 2. 6 minus 4 is 2, and 2 over 2 is 1. So the second solution for x is that x equals to 1 unit in its length. The radius of this semicircle, x equals to 1 unit in its length, according to the second solution. We only found out that line segment ZP equals to x minus 2 units in its length. So it is known. Line segment ZP equals to x minus 2 units in its length. ZP is a length, and as a length it must be a positive number. Actually, if x equals to 1, then ZP equals to x minus 2. So x minus 2 is 1, minus 2, that is minus 1. So I shall find out that the length of this line segment ZP is a negative. It's impossible, of course. Okay, again, ZP is a length, and as a length, it must be a positive number. Again, ZP equals to x minus 2. It is a length, and therefore as a length, it must be a positive number. What is a positive number? That is to say, it must be greater than 0. So, from this equation, we derive that x minus 2 must be greater than 0. We divide 2 to this inequality, and we get that x must be greater than 2. If x must be greater than 2, x can never be equal to 1. Because 1 is less than 2, so cancel the solution. And after with the first solution that is possible for x, that is actually x equals to 5 units in its time. So the radius x of the semicircle equals to 5 units in its time. Okay, again, the radius of this semicircle, that is the radius that we are looking for in this question, the radius x equals to 5 units in its time. So finish to answer the second question. In the next step, I summarize the lecture. That is to say, we repeat on the solution of the first question, and then we repeat on the solution of this second question. In the first question, our task was to find out the area of this green shape. So if we find out the area of this green shape by using two different methods. So in the drawing, we have rectangle ABCD. We know that this is line segment AE is equals to 1 unit in its length. One side of rectangle ABCD equals to 3 units in its length. That is to say, AB equals to 3. Inside this rectangle ABCD, we have this green shape. This is again BEC is equals to 45 degrees in its side. So, okay, again, our task is to find out the area of this green shape. So, we start with the first method. Repeat on the first method. Okay. Quadrilateral ABCD is a rectangle, and therefore those four angles are all right angles. This is an rectangle. We define the length of this line segment ED as x. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 3, therefore the opposite side DC must be also equal to 4 units in its length. Likewise, according to the symbol, in the same rectangle ABCD, side AD must be equal to the opposite side BC, but AD in total is 1 plus x, therefore the opposite side BC must be also equal to 1 plus x units in its length. In the next step, we did the construction, that is to say, from point A, we go perpendicular on BC. Again, from point A, we go perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. From point A and BC, this point is point S. By doing this construction, we get the quadrilateral ABSC. Inside quadrilateral ABSC, we have 1, 2, 3 degrees. and therefore this fourth missing must be equal to 90 degrees in its size. Again, repeat again, inside quadrant A, B, and C we have 400 degrees, and the sum of right angles is 270 degrees, so 270 degrees plus the size of this fourth missing, and so that the must be equal to 460 degrees. According to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth missing must be equal to 90 degrees in its size. So in quadrilateral A, B, and C we have 4 degrees, and therefore we can relate to quadrilateral A, B, and C is a rectangle. So A, B, and C is a rectangle, but also note the double, we define the length of ES as H, because it is the height to the base BC, or the rectangle B and C. So ES equals to H units in itself according to our definition. So in rectangle A, B, and C, side AB must be equal to double side ES. But AB is 3, therefore double side ES must be also equal to 4 units in itself. ES equals to H, and therefore H equals to 3. Okay. Our task is to find out the area of this green shape. What is the area of the green shape? The green shape is actually the green triangle EBC. So we have to find out the area of the green triangle EBC. But before that, we implemented the Pythagoras theorem on this upper green triangle BAE. This upper green triangle BAE, according to the Pythagoras theorem, in a triangle the square of the hypotenuse equals to the sum of the square of the perpendiculars. So in this upper triangle BAE, EB squared, that is the square of the hypotenuse, equals to AB squared plus AE squared. And again, in the right upper triangle AEB, EB squared, that is the square of the hypotenuse, equals to AE squared plus AB squared. EB is the missing side, so we leave this it is. And it equals to AE squared. A is 1, therefore A squared is 1 squared, that is 1, plus AB squared. AB is 3, therefore AB squared is 3 squared, that is 9. So total, actually found out that EB squared equals to 1 plus 9, that is 10. So EB squared equals to 10. Here we took out of this equation, and we found out that the missing hypotenuse EB equals to the square root of 10 units in its name. This is the hypotenuse EB, this equals to the square root of 10 units in its name. The next step we implemented the Pythagoras theorem on this triangle type EDC. This triangle EDC, according to the Pythagoras theorem, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. Repeat again, this right lower triangle EDC, according to the Pythagoras theorem, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. EC is the missing hypotenuse, so it is, and it equals to ED squared. ED is x, therefore ED squared is x squared plus DC squared. DC is 3, therefore DC squared is 3 squared, that is 9. So in total, we should know that EC squared equals to x squared plus 9. Here we took out all this equation, and we found out that the missing hypotenuse EC equals to the square root of x squared plus 9. In the next step, we calculated what is the area of the green shape. Is the area of the green triangle EBC. Area of this green triangle, area of the green shape, it is the area of this green triangle EBC. So we calculated the area of this green triangle EBC in 2 different methods. And then we created equation 3 that said that the area of this green triangle EBC according to the first method of calculation must be equal to the area of this same green triangle EBC according to the second method of calculation. In the first method, we calculated the area of this green triangle EBC according to the rule that said that the area of green triangle equals to the base of the triangle times the height to the base over 2. So the area of this green triangle EBC according to the first method of calculation must be equal to the base BC times the height edge over 2. According to the first method of calculation, the area of the green triangle EBC equals to the base BC times the height edge over 2. BC equals to 1 plus x times the height edge, this is 3 over 2. And again, the base BC equals to 1 plus x, edge is 3 over 2. So in total, we should find out that the area of the rectangle BCA according to the first method of calculation equals to 3 times 1 plus x over 2. In the next step, we calculated the area of this rectangle ABC according to the second method. So this is triangle ABC that could be an A triangle. Side AB equals to A units in itself, side AC equals to B units in itself, and the angle between those two sides is this angle that is theta. The area of this triangle ABC that could be any triangle equals to the multiplication of those two sides by each other, that is to say A times B, times sinus angle between those two sides, that is theta over 2. But again, in total, the area of this triangle ABC equals to A times B times sinus theta over 2. Therefore, the area of this triangle ABC equals to the multiplication of the two sides by each other, that is to say it is EB times EC times sinus angle between the two sides, that is sinus 45 degrees over 2. And again, the area of this triangle ABC according to the second method of calculation is equals to the multiplication of the two sides by each other, that is to say it is EB times EC times sinus angle between the two sides, that is 45 degrees, so it is sinus 45 degrees over 2. So the area of this triangle ABC according to the second method of calculation equals to EB times AC times sinus 45 degrees over 2. EB is square root of 10, EC is square root of x squared plus 9. And again, EB is square root of 10, EC is square root of x squared plus 9 times sinus 45 degrees over 2. So the area of the rectangle ABC according to the second method of calculation equals to square root of 10 times square root of x squared plus 9 times sinus 45 degrees over 2. Sinus 45 degrees is square root of 2 over 2. Then we created the equation 3 that said that the area of this rectangle ABC according to the first method of calculation must be equal to the area of this rectangle ABC according to the second method of calculation. Okay. This is equation 3 that said that the area of the rectangle ABC according to the first method of calculation must be equal to the area of triangle ABC according to the second method of calculation. The area of triangle ABC according to the first method of calculation equals to 3 times 1 plus x over 2, and it must be equal to the area of the triangle ABC according to the second method of calculation, and the area of the triangle ABC according to the second method of calculation equals to the square root of 10 times square root of x squared plus 9 times sinus 45 degrees over 2. Here we have 2 on both sides of the equation, so 2 will get cancelled. After cancelling 2, in this side of the equation we have only 3 plus 1 plus x, while on the other side of the equation we have only square root of 10 times square root of x squared plus 9 and sinus 45 degrees is square root of 2. Square root of 2 times 2. So 3 times 1 plus x equals to square root of 10 times square root of 2 is square root of 20, and we have also square root of x squared plus 9 over 2. We substitute 20 by 4 times 5, so in total 3 times 1 plus x equals to 20 is 4 times 5 times square root of x squared plus 9 over 2. The square root of 4 is 2, so we took 4 out of the root, and inside the root we left only 5. So today we should find out that 3 times 1 plus x equals to 2 was taken out of the root, so the square root of 4 is 2. Inside the root we left only 5 times square root of x squared plus 9 over 2. Here we have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. After we cancel 2, in the side of the equation we have only square root of 2 times square root of 5 times square root of x squared plus 9 equals to 3 over 1 plus x. Again, according to equation 3, we have found out that 3 times 1 plus x equals to the square root of 5 times square square root of x squared plus 9. If we square both sides of this equation, equation 3, if I found out that 3 squared is 9 times 1 plus x squared equals to the square root of 5 squared is 5, and the square root of x squared plus 9 squared equals to x squared plus 9. The square cancels the root, and we left only x squared plus 9. So in total, according to equation 3, we should find out that 9 times 1 plus x squared equals to 5 times x squared plus 9. Here we open the brackets on both sides of this equation. So here we have 9 times 1 plus x squared. 1 plus x squared equals to 1 squared. This is 1 plus x squared plus 2 times 1 times x, this is 2x. And it equals to 5 times x squared is 5x squared. Plus 5 times 9 is 45. Open the brackets on this side of the equation, equation 3. We should find out that 9 times 1 is 9. Plus 9 times x squared is 9x squared. Plus 9 times 12 is 18x, and it equals to 5x squared plus 45. Here we subtract the 5x squared from this equation. So 9x squared minus 5x squared is 4x squared. Plus 9 plus 18x equals to 45. Here we subtract 45 from this equation, equation 3, and we found out that 4x squared plus 18x, and we have 9 minus 45 is minus 36 equals to 0. Okay. So in total, we found out that 4x squared plus 18x minus 46 equals to 0. Here we divide this equation 3 by 4, and finally found out that 4x squared over 4 is x squared, 18x over 4 is 4.5x, and minus 36 over 4 is minus 9 equals to 0 over 4 is 0. So to that, we should find out that x squared plus 4.5x minus 9 equals to 0. So this is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that you are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus 4 to b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say ax squared plus 4.5x minus 9 equals to 0. The variable that you're looking for is x. The coefficient a equals to 1, the coefficient b equals to 4.5, the coefficient c equals to minus 9. So now to find out the value of x, that is the variable that we're looking for, in our specific quadratic equation, we just have to put the data of this quadratic equation, the data inside this general formula for x. This way we find out the value of the values of x, because x might have also more than one solution. So we did it, and we found out that x equals to minus b. B is 4.5, therefore minus b is minus 4.5, plus minus square root of b squared. B is 4.5, therefore b squared is 4.5, that is 20.25. Minus 4 times a times c, so a is 1, so minus 4 times 1 is minus 4 times c. C is minus 9, and minus 4 times minus 9 is plus 36. So inside the root we have 20.25 plus 36 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, we found out that x equals to minus 4.5 plus minus 20.25 plus 36 is 56.25. So inside the root we left only 56.25 divided by 2. So if we found out that x equals to minus 4 plus minus, the square root of 56.25 is 7.5 over 2. So here we have two solutions that are possible for x. The first solution for x is that x is equals to minus 4.5 minus 7.5 over 2. Minus 4.5 minus 7.5 is minus 12 over 2. Minus 12 over 2 is minus 6. And because of the fact that x is the length of line segment ED, x is the length, it must be a positive number. It can never be equal to minus 6, it is a negative number. So the first solution for x is incorrect solution. We took into account only the second solution for x. The second solution for x is as follows: x equals to minus minus 4.5 plus 7.5 over 2. Minus 4.5 plus 7.5 is 3. Total x equals to 3 halves. That is 1.5. So x it is equals to x equals to 1.5 units in its name. Our task is to find out the area of this green shape. The green shape is actually the green triangle ABC. The area of this green triangle ABC equals to the base BC times the height edge over 2. And again, the green shape is actually the green triangle EBC. The area of the green triangle EBC equals to the base times the height over 2. That is the area of green triangle. We choose the base as BC, the height is h over 2. BC is 1 plus x times the height edge is 3 over 2. X is 1.5. We found out that x equals to 1.5 units in itself, and therefore x plus 1 is 1.5 plus 1, that is 2.5 times 3 over 2. 2.5 times 3 is 7.5. 7.5 over 2 is 3.75 square units in size. So she found out that the area of this green shape equals to 3.75 square units in size. So we finish with the first method. The next time I present to do how to find out the area of this green shape according to the second method. Again, ABCD is right angle, therefore all those four angles are all right angles. We define the ref of ED as x. We also know that the opposite sides of right angle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 3, therefore the opposite side DC must be also equal to 3 units in its length. Likewise, according to the sum rule in the sum rectangle ABCD, side AD must be equal to the opposite side BC. AD in total is 1 plus x, therefore the opposite side BC must be also equal to 1 plus x units in its length. In the next step we did the construction, that is to say, from point E we draw perpendicular on BC. Again, from point E we draw perpendicular on BC, or side BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching points of the perpendicular from point A and BC. From point E and BC, this point is point S. When doing this construction, we added the small polygonal ABAC. Inside the small polygonal ABAC, we have 1, 2, 3 angles. The sum of 3 angles is 230 degrees, so 230 degrees plus the size of this surface area, in total must be equal to 360 degrees. According to the rule, it said that the sum of the angles in any polygonal is equal to 360 degrees. Therefore, this surface area must be equal to 90 degrees in its size. So in polygonal ABAC we have 4 right angles, therefore we can relate to polygonal ABAC as a right angle. But we also know that the opposite sides of right angle are equal to each other. So in right angle ABAC, side AB must be equal to the opposite side SE. But AB is 3, therefore the opposite side SE must be also equal to 3 units in its length. We define SE as h, therefore SE equals to h equals to 3. So we did all the things that I presented you. We already done in the first method. The second method, we define this angle AEB as theta. So in the right triangle, upper right triangle AEB, triangle theta equals to AB over AE. In the right upper triangle ABE, triangle theta equals to AB over AE. AB is 3, AE is 1. So in total, AB equals to, triangle theta equals to 3 over 1, that is 3. So according to equation 1, we will know that triangle theta equals to 3. Then we use the trigonometric identity that says that triangle theta plus 45 degrees equals to 1 plus triangle theta over 1 minus triangle theta. So according to this trigonometric identity, triangle theta plus 45 degrees equals to 1 plus triangle theta. Triangle theta is 3, so substitute triangle theta by 3. So it is in the numerator over 1 plus 3 over 1 minus triangle theta. Again, triangle theta is 3, therefore substitute triangle theta by 3. So total, we found out that triangle theta plus 45 degrees equals to 1 plus 3, that is 4, or over 1 minus 3, this is minus 2. So in total, tangent theta equals to 4 over minus 2, this is minus 2. So according to equation 2, if you found out that tangent theta plus 45 degrees equals to minus 2, but according to equation 1, we only found out that tangent theta equals to 3. AD is one side of parallel ABCD, the point is absolutely straight line. So if you focus on the right side of the straight line AD at point D, here the sum of the areas must be equal to 180 degrees. According to the rule that says that the sum of the areas from one side, all three, that says that the sum of the areas from one side of the straight line is equal to 180 degrees. So which areas we have at the right side of the straight line AD at point D, we have this area that is theta, plus this area that is 45 degrees, plus this third area, that must be equal to 180 degrees according to all three. Therefore this third area must be equal to 180 degrees minus theta plus 45 degrees, because in total the sum of those areas is 180 degrees. So 180 degrees minus the sum of those areas is 180 degrees minus theta plus 45 degrees. So this third area must be equal to 180 degrees minus theta plus 45 degrees. So in this right lower triangle ADC, tangents 180 degrees minus theta plus 45 degrees equals to DC over AD. In right triangle ADC, tangents 180 degrees minus theta plus 45 degrees equals to DC over AD. DC is 3, AD is x. So in total, tangent theta equals to 3 over x. The tangent 180 degrees minus theta plus 45 degrees equals to 3 over x. We have the trigonometric identity that says that tangent 180 degrees minus theta equals to minus tangent theta. So according to this trigonometric identity, tangents 180 degrees minus theta plus 45 degrees equals to tangent theta plus 45 degrees. Okay? And it equals to 3 over x. So we have minus tangents theta plus 45 degrees minus tangent theta plus 45 degrees equals to 3 over x. But we already found out that tangent theta plus 45 degrees equals to minus 2. So we substitute tangent theta plus 45 degrees by minus 2. So in total, in this side of the equation, we have minus 2 is equals to 3 over x. Minus times minus is plus, so minus 2 is plus 2 is equals to 3 over x. Here again, according to equation 3, we found out that 2 equals to 3 over x. Here we multiply this equation 3 by x and finally found out that 2x equals to 3. Here we divide this equation 3 by 2 and finally found out that x equals to 3 offset is 1.5. Therefore, plus and ed equals to x equals to 1.5 units in itself. Our test is to find out the area of this green shape. The green shape is actually the area of this green triangle ABC. Okay. The area of the green shape equals to the area of the green triangle ABC. The area of the triangle equals to the base of the triangle times the height over 2. So the area of this green triangle ABC equals to the base BC times the height edge over 2. The area of the green triangle ABC equals to the base BC times the height edge over 2. BC equals to x plus 1. X is 1.5, therefore x plus 1 is 1.5 plus 1, that is 2.5. So BC is 2.5 times the height edge is 3 over 2. So in total, the green shape equals to the base BC, that is 2.5 times the height edge, that is 3 over 2. 2.5 times 3 is 7.5. 7.5 over 2 is 3.75 squares in size. So in both methods, we have found out that the area that we are looking for this equation, that is the area of this green shape, is equals to 3.75 squares in size. We finish with the repetition of the first question. In the next step, I repeat on the solution of the second question. second question, our task is to find out the radius of this semicircle. So in the drawing, we have rectangle ABCD. Inside this rectangle ABCD, we have this semicircle. Again, our task is to find out the radius of this semicircle. In addition, we know that this is line segment QV, this is equal to 1 unit in itself. This is line segment PD, this is equal to 2 units in itself. Again, our task is to find out the radius of this semicircle. First of all, it is given as a question that ABCD is a rectangle, therefore those four angles are all right angles. In the next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as R. So OP is the radius of this semicircle. We define the radius of this semicircle as X. So the radius of OP equals to X. The radius of OQ equals to X also. In the next step, we did the construction, that is to say, first of all, we define the point of tendency of tangent DC with this semicircle. This point is point H. Likewise, we define the point of tendency of tangent BC with this semicircle. This point is point T. And then we add, we join points O and H together by side line. Point O is the center of this semicircle. Point H is the point of the semicircle itself. Therefore, OH is the radius of this semicircle equals to X. The radius of OH is equals to X. The radius of OH is 1 to point H, that is the point of tendency of tangent DC with this semicircle. And whenever you have radius that is 1 to the point of tendency, then tangent DC will be perpendicular to the radius HO. If DC is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and T together by side line. OT is the radius of this semicircle equals to X. The radius of OT is equals to X. The radius of OT is 1 to point T, that is the point of tendency of tangent BC with this semicircle. Whenever you have a radius that is 1 to the point of tendency, then tangent BC will be perpendicular to the radius TO. If BC is perpendicular to TO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the sum rule 1. So in quadrangle OHCT we have 1, 2 furthers. Therefore this fourth angle must be equal to 90 degrees in size. So according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. So in quadrangle OTCH we have 4 angles, and therefore we can relate to quadrangle OTCH as a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle OTCH, side OH must be equal to the opposite side TC. But OH is X, therefore the opposite side TC must be also equal to X units in its length. Likewise, according to the sum rule, in the same rectangle OTCH, side OT must be equal to the opposite side HC. But OT is X, therefore the opposite side HC must be also equal to X units in its length. So we should find out that quadrangle OTCH is not a rectangle but a square, because of the fact that all of its sides are equal to each other, each side equals to X. The next step, we did the construction, that is to say, from point O, that is the center of this semicircle, we go perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point L. By doing this construction, we get the quadrangle LOTB. Inside quadrangle LOTB, we have 1, 2 furthers. Therefore, this fourth angle must be equal to 90 degrees in size. According to the sum that says that the sum of the angles in any quadrangle is equal to 360 degrees. So in quadrangle LBTO, we have 4 angles, and therefore we can relate to quadrangle LBTO as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle LBTO, side TO must be equal to the opposite side LB. But TO is X, therefore the opposite side LB must be also equal to X units in its length. But what is the length of this line segment LQ? LQ equals to LB minus QB. And again, LQ equals to LB minus QB. So LQ equals to LB, that is X, minus QB, that is 1. So in total, LQ equals to X minus 1 units in its length. In the next step, we did another construction, that is to say, from point O, we do perpendicular on AD. Again, from point O, we do perpendicular on AD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AD. This point is point Z. Okay. And in this construction, we get there another rectangle. But if you focus on the lower quadrangle ZOHD, inside the lower quadrangle ZOHD, we have 1, 2, 3 rectangles. Therefore, this fourth angle must be equal to 90 degrees inside according to the sum that Z is the sum of the angles in the quadrangle is equal to 360 degrees. Therefore, quadrangle ZOHD we have 4 angles, and therefore quadrangle ZOHD is a rectangle because it has 4 angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the lower rectangle ZOHD, side OH must be equal to the opposite side ZD. But OH is x, therefore the opposite side ZD must be also equal to x units in its length. What is the length of this short line side ZP? ZP equals to ZD minus PD. ZP equals to ZD minus PD. So ZP equals to ZD, this is x, minus PD, this is 2. So in total, we should find out that the short line side ZP equals to x minus 2 units in its length. Okay. This is angle ZOT. Angle ZOT equals to 90 degrees plus 90 degrees. It is 180 degrees. Okay, again, this is angle ZOT. It is equals to 180 degrees in its size. And you know that any angle is equals to 180 degrees in its size, it is defined as a straight line. Angle ZOT equals 280 degrees in its side, therefore angle ZOT, line 7 ZOT is a straight line. If ZOT is a straight line, then ZT is also a straight line. ZT is a straight line, and therefore this is shape ABTZ. In shape ADTZ consists of 4 sides. 1, 2, 3, 4. Okay. Shape Z ABTZ total consists of 4 sides. Therefore, shape ABTZ is a quadrilateral. Again, shape ABTZ is a quadrilateral. But in quadrilateral ABTZ, we have 1, 2, 3, 4 right angles. And any quadrilateral that has 4 right angles must be this rectangle if not a square. So we refer to quadrilateral ABTZ as a rectangle. Quadrilateral ABTZ is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are parallel to each other. So rectangle ABTZ, side AB is parallel to the opposite side ZT. And again, in the upper rectangle, upper spot rectangle ABTZ, side AB is parallel to the opposite side TZ. AB is parallel to ZT. Those two angles are defined as corresponding angles and are located between the parallel lines AB and ZT, and therefore they must be equal to each other, the sizes according to rule 10. So those two angles are equal to each other, the sizes according to rule 10. So if we find the size of this angle as alpha, then the size of this angle must be also equal to alpha according to rule 10. So they are equal to each other according to rule 10. So in the upper triangle L or Q, this angle equals to alpha according to rule 10, this angle equals to 90 degrees according to construction. Therefore, this first angle must equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. It is the sum of the angles in a triangle. Likewise, in the lower triangle OZP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha according to the sum that said that the sum of the angles in a triangle is equal to 180 degrees. The next step we proved that those two right angles can go into each other according to angle, side angle rule. So why those two right angles can go into each other? First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, QO equals to OP, they are both they have the same second equals to x, and therefore they are equal to each other. And finally, those two angles are both equal to 90 x minus half, and therefore they are equal to each other. So if you found out that those two right-angled triangles can go into each other according to angle side angle rule. And again, if you found out that the right upper triangle LOQ can go into the right lower triangle ZPO according to angle side angle rule. That is to say, if you found out that those two angles and the side that is included between those two angles, that is side QO, and this upper right triangle LQO corresponding equal to those two angles, and the side that is included between those two angles, that is side OP, this lower right triangle ZOP. Therefore, those two right triangles can go into each other according to angle side angle rule. From the fact that those two right triangles can go into each other, we will derive that their corresponding sides must be also equal to each other in their lengths. That is to say, NQ equals to ZO. Again, according to the rule that said that the corresponding angles in congruent triangles are equal to each other, we found out that LQ equals to its corresponding side OZ. LQ is the corresponding side of OZ because of the fact that both those two sides are located in front of angle 90 degrees minus alpha, and therefore the corresponding sides. LQ equals to ZO, but LQ is x minus 1, so we can write that LQ equals to x minus 1, and from this equation x minus 1 equals to LQ equals to ZO, we will write that ZO must be also equal to x minus 1 units in there. This is the missing side, the ZO equals to x minus 1 units in there. What is the length of this short line side ZP? ZP equals to ZD minus PD. Again, ZP equals to ZD minus PD. So ZP equals in total to ZD, this is x, minus PD, this is 2. So in total, this is the missing line side ZP, this is equals to x minus 2 units in its length. In the next time we implement the Pythagoras theorem on this right lower triangle, OZP. According to the Pythagoras theorem, this right triangle OZP, OP squared, that is the square of the opponent, equals to OZ squared plus ZP squared. Then again, right lower triangle OP, OP squared, that is the square of the opponent, equals to OZ squared plus ZP squared. OP is x, therefore OP squared is x squared, it is equals to OZ squared. OZ is x minus 1, therefore OZ squared is x minus 1 squared. Plus ZP squared. ZP is x minus 2, therefore ZP squared is x minus 2 squared. So in total, we should all know that x squared equals to x minus 1 squared plus x minus 2 squared. Open the brackets of this side of this equation, and find out that x squared equals to x minus 1 squared, that is x squared plus 1 squared, that is 1, minus 2 times x times 2, minus 2 times x times 1, that is minus 2x, plus x minus 2 squared. X minus 2 squared equals to x squared, plus 2 squared, that is 4, minus 2 times x times 2, that is minus 4x. Here we have x from both sides of this equation, so x squared will cancel x squared on this side of the equation left with nothing, that is to say 0, while on the other side of the equation, we have 1 plus 4 is 5, minus 2x minus 4x is minus 6x, plus x squared equals to 0. So we should find out that x squared minus 6x plus 5 equals to 0. So this is a quadratic equation. And the general form of a quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared minus 6x plus 5 equals to 0, the variable that we are looking for is x. The coefficient a equals to 1, the coefficient b equals to minus 6, and the coefficient c equals to 5. The only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x, and in this way we find out the value of the values of x, right? Because x could have two solutions. So we did it, and we found out that x equals to minus b. B is minus 6, therefore minus b is minus 6, that is plus 6, plus minus square root of b plus minus square root of b squared minus 4 times a times c. So it is plus minus b squared. B is minus 6, therefore b squared is minus 6 squared, that is 36, minus 4 times a times c. So it is minus 4 times a. A is also minus 4 times 1 is minus 4 times c. C is minus 6, C is 5, so minus 4 times 5 is minus 20. So inside the root, in total we have 36 minus 20 over 2a. A is 1, so 2a is 2 times 1, that is 2. So x equals to 6 plus minus 36 minus 20 is 16, so inside the root we have to only with 16 over 2. So total x equals to 6 plus minus, the root of 16 is 4 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to x plus 4 over 2. X plus 4 is 10 and 10 over 2 is 5. So the first solution for x is that x equals to 5. We have another solution for x. The other solution for x is as follows. X equals to 6 minus 4 over 2. 6 minus 4 is 2 and 2 over 2 is 1. So the second solution for x is that x equals to 1 unit in interim. Zp equals to x minus 2. Therefore, short answer is Zp equals to x minus 2. Zp equals to x minus 2. So if x is 1, then x minus 2 is 1 minus 2, then it's negative. Although that the roof of Zp is a negative number, that is impossible. Therefore, it is impossible. Another way to prove that x can never be equal to 1 is that because of the fact that Zp equals to x minus 2, Zp is a length. Zp is a length, and it's a length, it must be a positive number. And again, from this short answer, Zp equals to x minus 2. Zp is a length, and it's a length, it must be a positive number. That is to say, it must be greater than 0. That is to say, x minus 2 must be greater than 0. Here we added 2 to this inequality and found out that x must be greater than 2. If x must be greater than 2, x can never be equal to 1, that is less than 2. So we cancel the solution, x can never be equal to 1, and we left only the other solution that is left, that is x equals to 5 units in its length. So we found out that the radius that we are looking for this equation, that is the radius of this semicircle equals to 5 units in its length. The radius x equals to 5 units in its length. Okay, thank you very much.